Yeah. I want to take golf. Somebody took the other. What? Oh yeah, that's right. Yeah.
All right, folks. Ready to try another example? Yes, let's do it. Oh, good. All right. So here's the recommendation. We're going to follow through this whole process. Let's go ahead and begin by coming over here to the right and just writing down a box that says U, D, easier, not worse. Because that kind of, you already have started the process, you're feeling pretty good about yourself, like, all right, I'm halfway done. They're drawing your little box. Now, we want to take this integral. I'm going to start by writing it down in my own handwriting. So the integral of 6x e to the 4x. Although, what am I going to do with that 6? Just take it outside, leave it there for a while. So we have x e to 4x dx. And the idea is that we're going to choose the first part to be u and the second part to be dv. So there's u and there's dv.
Where do we know where to cut it in the middle, I guess?
Well, one good thought would be wherever you'd see the multiplication dot. Great question, Warren. Because this is somewhat arbitrary. Because if it's written down like this, you'd say, well, okay, the first part of the product is x, and then the last part of the product is e to the 4x, and the dx is at the end, so it goes with this part, the dv. But like to Juan's point, what if somebody had given me this integral, and they had just as easily written down e to the 4x times x dx? Then in that case, you might have labeled that as u, and that as dv. You see? So both of these are correct ways of labeling u and dv, but only this way is going to work, and this way will end in utter failure. Right? And so, and that's part of math, is sometimes you try one way, it doesn't work, so you go and try the other way. I'm having us try the correct way first. Yeah?
Will there be problems that you
give us where it'll be laid out in a way that wouldn't be wrong if we just split it out?
Maybe. Yeah, I mean, to Juan's point, how do you know? You don't know. You just try, because there's only two ways to write down even x times e to the 4x. You either write it down with x first, or you write it down with e to the 4x first. Either way, the dx is at the end, part of the second part. And the first part is, whichever one. You just try one, and see if it works. There is, though, what I have down here written for you, is that if you chose the right way, then this way should get easier, and this way should get not worse. And if you choose the wrong way, this side is going to get worse. And then you're going to say, oh, I chose the wrong way because it got worse. So let's do the right way first. Okay, so here we are. We chose this. Let's go ahead and label in. U is x, and dv is e to the 4x dx. Okay, so now let's fill in our box. And we started over there. We tried the labeling. We're going to go over here now. So over here, the left-hand side, I'm taking the derivative. Remember, you take the derivative going down. Because we're going from u to du, so we must be taking the derivative. So the derivative of x is dx. What? Oh, okay, yeah, dx. And then on the other hand, over here, this is already the derivative, so I need to go back up and take the antiderivative. So the antiderivative of dv is v, and the antiderivative of e to the 4x dx is just e to the 4x. Actually, no, it's not. What's the antiderivative of e to the 4x? It's a toolkit. The antiderivative of e to the 4x, 1 over 4 e to the 4x. Now, it's a coefficient, right? And yeah, the coefficient does look worse because it's 1/4, but it's merely a coefficient. The function itself didn't get worse. Coefficients are always not our concern because coefficients can just sit out front doing nothing. Okay, so we've got our parts. Now we come back and recall we still have a 6 out front. We're just leaving that alone. And we're now going to write down our formula. So the formula is u dv equals uv minus integral v u. I made a conscious effort to spread that out. You should also make a conscious effort to spread it out. Because if you just write down uv and v du, it's very tiny. But we're about to put everything over there underneath it. So you want to spread out so that you can put term by term by term, part by part underneath it. So, I'm just going to ignore the second one out. So, over here, I'm doing the integral of u, which is really x, dv, which is really e to the 4x dx. And is that indeed my original integral? Yeah, except for the 6. Yes, it is. Okay, so now I'm going to put in my other parts here. U is really x, and v is really 1/4 e to the 4x. And keep in mind, the part that I just wrote down, this uv, it's done. You don't have to take the integral of that. It's just done. That's just the answer. Nothing else needs to be done with this other than cleaning it up. You can write 1/4 x e to the 4x. Okay, so now we do the integral of v, which is 1/4 e to the 4x, and du, which is simply dx. So what do you think? Did conceptually everything work out? Our original integral was indeed hard. We did not have a formula for it yet. This is now done. We don't have to do anything else to it. And now this integral is easy. Right, because that integral is just e to the 4x. And we have a formula for that. So what's our answer now? We're going to do a little cleanup. This is 1/4 x e to the 4x minus, what's the antiderivative of e to the 4x? You have to divide by 4 again. There's already a 1/4 here. So if I divide by 4 again, what do I get? And 1/16 e to the 4x plus. And we're done. That is the integral of x e to the 4x dx. And so if I wanted to rewrite this whole thing here, the integral of x e to the 4x dx, that was the original problem, is equal to all that. But what integral were we actually doing? There was actually 6 there. So to the extent that I'm going to take this whole thing, put a 6 in front of it, I'm now going to take this whole thing and put a 6 in front of it. So that 6 coefficient was just kind of an afterthought we put on there afterwards. And now we can distribute that 6. If you distribute the 6, you now have 6/4, which is 3/2 x e to the 4x, minus 6/16, which is really 3/8 e to the 4x plus c. Again, c is just c. Even if you multiply it times the number, it's still just a constant. Because remember, that constant could be 0. We're just saying, hey, there could be a number there. Okay, so is that the correct answer? Who could we ask? Let's ask him. Integral, or her, I don't know if it's a her. Integral of 6x e to the 4x. I have no idea. Is that where you can see it? Yeah. Oh. Boy, these PCs sure are smart. Always assuming they know what I want. I didn't tell it what I wanted. Why does it make all these assumptions? All right, so the answer they gave was 3/8 e to the 4x times 4x minus 1. Is that the same answer? They clearly factored something out. So what did they factor out? Maybe better, easier to just distribute in. So if I distribute in, that would be 3 times 4 is 12/8 x e to the 4x minus 3/8 e to the 4x plus a constant. And 12/8 is really 3x. So do we have the same answer as Wolfram? Yeah. Okay, now Wolfram is just nice and convenient. You can check your answer yourself by taking the derivative. Okay. Now, Juan asked a very helpful question at the very beginning. He said, well, how do I know it's not this one? So everybody watch. Let's say that we assumed that this was the way we write the product. So watch, as I make my box, and I fill everything in now with my u, du, and dv, and v. My u is e to the 4x, and my dv is x dx. Now watch, this is the big clincher here. The derivative of u, well, that's easy. That's just 4 e to the 4x. Did it get easier? Well, I mean, I don't know. It didn't exactly get easier. It didn't get worse. It stayed the same, kind of. But now, what's the antiderivative of x? The antiderivative of x, first you'd add 1 and divide by what you get. So that'd be 1/2 x squared. A parabola is worse than a linear function. This is definitely worse, right? Nobody wants to deal with x squared if you could be dealing with x. So for sure, that got worse. And that's what tells me this was the wrong way to do it. Juan, does that answer your question? Yeah. Yeah. Because now watch. Let's just say that I wasn't even paying attention to easier and worse, not worse. And if I proceeded from here to say, okay, well, what does that do for me? What does that do for me? Well, now I started with the integral e to the 4x x dx. And now that becomes uv, so that's 1/2 x squared e to the 4x, minus the integral of v, which is 1/2 x squared, times du, that's u, which is 4 e to the 4x. Look at that integral that I now have to do. Compare this integral with that one. Which one would you rather do? This one. Okay, that definitely got worse. Like, I'm in no better position now to integrate this. I'm, in fact, in the worst position to integrate that. So that's why, given two choices of how to order them, we have this idea of this side should get easier and this side should get not worse. And provided you're following that rubric, then this integral that you end up with should be something easy enough that's in our toolkit already. Okay? So there, we would call that a false start. We chose the wrong way to label it. Now, you see that next problem, number 3? We're going to hold off on that. I would like us to do a couple more normal examples of the integration by parts, and then we will try number 3. So here we go. Let's do number 4. It's a wonderful example with everything that we've already done. So let's take a look. What's the first thing we're going to do? William, let me draw a box. There's a lot of first things we can do. Give ourselves a little progress. Feel like we're moving along. Okay, in this integral, what's the first thing we do? 3/2. Yeah, let's bring that 2 outside. Also, yeah, this is actually a definite integral, meaning when we're all done, we have to get an answer. But for right now, our main goal is to simply do the integral. So we can kind of hold off on that 1 to the e. And let's just focus on actually doing the antiderivative for now. Okay, let's just try to find the antiderivative. So to that extent, we can just focus on this. Right, the 2 we can multiply in later, and the 1 to the e, those are limits we're going to plug in later. But let's just try to do integration by parts on this. So how should we write it? Should we write it as t squared natural log t, or should it actually be natural log t, t squared? What should be the correct way of labeling u dv or u dv? Well, just looking at it, we have no idea. Right? How do we make the decision? By doing the box. Right? So let's just keep going with the way they wrote it. You know, might as well begin with the way they wrote it. Let's try the way they wrote it and come over here and actually write it down now. So u is t squared, and dv is natural log t dv, or dt. Well, on the one hand, if this is how we start the problem, then the derivative of t squared is simply 2t dt. Is that better? Yeah. Better. But on the other hand, going back this way, we have to take the antiderivative of natural log t. And I know I told you the formula for that last time, but we haven't actually proved the formula yet. And the formula for that, natural log x dx, is actually x natural log x minus x. And so if I wrote down here t natural log t minus t, is that worse? Yeah, it's actually worse. Plus, theoretically, we don't even know the answer to the integral of natural log z until we do number 3. So just looking at this then, the idea would be, even though that got better, this got worse. So this was actually the wrong way. Okay? So I apologize, we're not going to do this one. That was another dead end. That was like, well, that one didn't get better, but this side got much worse. So this is not the way to go. So I'm just going to erase it on my whiteboard. I'm sorry, you might have to scribble or erase, or whatever you want to do. So now let's write it the other way. And we're actually going to do the integral of natural log t times t squared. Okay, so now we'll say this is u and this is dv. Well, let's try our box again. Okay. So now we have the natural log t first and the t squared second. Let's see what happens now if I plug in my natural log t there, and then t squared dt here. Now if I do take the derivative of natural log t, what's that?
1 over t.
Yeah, 1 over t dt. Is that better or worse? Well, I mean, I guess it's a little better because it's not a natural log anymore. It's just a variable. Now, on the other hand, over here, we're going to go this way, take the antiderivative. Then you'd add 1 and divide by what you get. And on the one hand, we might be feeling like, well, that's a little worse because we're going from a squared to a cubed. But on the other hand, it's still just a power function. You know, it's not significantly worse. It's still just a power function. And more importantly, let's see where this leads. Okay, so let's see what happens. So now what I have here is we write down the formula. Again, write it down very big. U dv equals u v minus v u. This whole idea that I gave you up here saying it should be easier and it should be not significantly worse. This is kind of an early litmus test to see if what you're doing is going to be good or not. The real litmus test is we're starting with an integral that we can't do. And we should end up with an integral that we can do. That's how you really know that you made the right choice of what's u and what's dv. So let's take a look now as we plug in all these parts and pieces from that table. Because The first way we did it, oh gosh, I can do this from just memory, t squared natural log dt. The first way we did it would have been yeah, that's what would have happened the first way. The first way, we were going to take the integral of it this way. That's already done, and we would have ended up with this. I hope you all can see that that's significantly worse. Because we started with just a natural log t times a t squared. Now we have a natural log t times t cubed. When you distribute that in, now we end up with an integral of t cubed natural log t minus t cubed. So we went from this one, which was just natural log times t squared. Now we have natural log times t cubed minus the t cubed. This is way worse. And that's why that first one was a no-go. So that other way was a no-go. Whereas now look what happens when we plug in all these numbers. Not numbers, but functions. Now we have integral of u, which is natural log, times dv, which was t squared dt. And sure enough, that was the original integral, the way we wrote it. Then we have uv, so that's u times v is natural log t times 1/3 t cubed. I'm going to write 1/3 t cubed natural log t. Is that okay that I just write backwards? Because uv you can write down as vu. Okay, now minus the integral of v, which is 1/3 t cubed, times du, which is 1/t dt. So now, looking at this again, the original one we can't do. We don't know how to do it. This one, can we do that? Now, why can't we? What are we going to do first? This is t cubed divided by t. What does that become? It's just t squared. This is just 1/3 t squared. And that is definitely an integral that we can do. So we have 1/3 t cubed, natural log t, minus the integral of 1/3 t squared dt. That's definitely in our toolkit. So look what happened. By doing this choice of writing natural log t first and t squared second, we yielded an integration by parts table that when we filled it into the formula, we got from a hard integral that we couldn't do to an easier integral that we could do. So now we simply take that integral. So now the answer is 1/3 t cubed natural log t minus add 1, that's t cubed, and divide by what you get. So that'd be 1/9. That's it. Plus c. Right. Okay, so everything that we just did was simply to come up with the antiderivative of the original. Now we have to put back in our 2, and we have to do the fundamental theorem of calculus by plugging in our limits of 1. But just that, how does everyone feel? We got to 1/3 t cubed natural log t minus 1/9 t cubed plus c.
You didn't put the
Well, no, we did the integral. We just did the integral right now. We added 1 and divided by what we got, so that was the integral. Okay, now according to Wolfram Alpha would probably factor out the t cubed and a 1/3, and they would have 1/3 natural log, 1/3 t cubed outside of 1/3 t cubed outside of natural log t minus 1/3. Let's just check our answer before we keep going. Is that what Wolfram says? Integral of t squared times natural log t. I should probably use x, not t. Okay, it worked. Hey, did we get it? They said they factored out 1/9 t cubed times 3 log minus 1. Is that the same?
No.
Yeah, I could have factored out a 1/9 as well. If I take out another third, then that would be 1/9 out there, and then that'd be 3 minus 1. So did we get the same answer? Yeah. So we agreed with Wolfram. That's our answer. I'm going to keep, well, it doesn't matter which way you keep. I'm just going to keep the way we did it. So now that we're done, let's write down the original problem. So everybody, you'll need a little bit of extra space here. The original problem was 2 times the integral of 1 to e of t squared natural log of t dt. And we just found out that that is equal to 2 times 1/3 t cubed natural log t minus 1/9 t cubed, evaluated from 1 to e. Now I realize I started by writing a plus c because that was an indefinite integral that we were just playing with. But we're actually doing a definite integral from 1 to e, so you don't have the plus c anymore. And did we do that correctly? When you do the fundamental theorem of calculus, you replace the antiderivative, or replace the integral with the antiderivative, and then we're going to plug in e and 1 and subtract. Everybody feel okay with this? So then we would have 2, this is going to be a lot, something minus something, where we first write down the first structure, which is 1/3 something cubed natural log of something minus 1/9 something cubed. And then the same structure, 1/3 something cubed natural log of something minus 1/9 something cubed. And here we're plugging in an e, and here we're plugging in a 1. This is quite a lot of structure, isn't it? Now, folks, to be fair, everything that's inside that parenthesis now is just arithmetic. Right? You just plug it all into your calculator and you get it. So to be fair, it's not technically hard. It's just a lot. Right? It's just a lot. It's just a lot to do, especially when you go to type all that structure in. So everybody, try to type in the first structure into your calculator. What would that look like in your calculator? That structure right there would be parenthesis 1/3 parenthesis parenthesis e to the power of 3 parenthesis parenthesis natural log parenthesis e parenthesis minus parenthesis 1/9 parenthesis parenthesis e to the power of 3 parenthesis. I did. Anyway. There, everybody try typing that in. Right, it's 1/3 e cubed times natural log of minus 1/9 e cubed. Yep, that's all of it. Now the important thing about writing in that structure once is that once you have it once, you can just hit second enter, and you're going to do that whole thing again, but plugging a 1 where the e was. So 1. Here. 1. And keep in mind, it really is natural log. Natural log of e. Notice that when you call up the e function, it automatically gives you a caret. So if you just want the number e, you're going to put in e to the 1. So far, did you get 4.6730? When you go back to edit to put in the 1, you'll have to actually erase the e and put in 1 to the.
I think it worked.
You didn't? What did you get? What's mine? I'm gonna get the answer here real quick, so we can all compare. Second part. Yeah, boy. Okay, I must have really typed something in incorrectly. Oh, I did. I got negative 8.24. Russell, was that what you got? Or Henry, is that what you got? Okay, no, it's okay.
I think it's negative, right?
Oh, but I didn't multiply everything by 2 yet. Oh, but that would make my first answer correct.
Yeah. I like your first answer.
Yeah, 4.673. But then I would still have to subtract 9 times 2. What does it say? I seem to be a little off. Okay, I need to really look at my calculator. Boy, this is like the trickiest part. Is maybe it would have been helpful to actually simplify this a little bit before typing in all that structure. Like for instance, it's 1/3 t cubed natural log t minus 1/9 t cubed. So this would actually be 1/3 e cubed. And what's the natural log of e, people? E to the what is e? 1. So that's just 1. I'll just take rid of that. So 1/3 e cubed minus 1/9 e cubed. So that's actually my first part. And then minus, what's the natural log of 1? E to the what is 1? E to the 0. So that's 0 times that is 0. So that's just minus 1/9. So that's minus 1/9. So that's plus 1/9. So far that's what I have, and that whole thing is times 2. So let me try that again. If I have E. Okay. All right. That is correct. That's the actual answer. Oh, folks, I feel so sad when something like this happens. This is such complicated minutia at the end, typing everything in to get an answer. The answer is 9.149. 9.14947. And that's what Desmos gave. So we did get there. It's just a matter of being so darn careful when you type everything into your calculator so that you can actually get the answer. And, you know, for the sake of learning integration by parts, we probably could have just stopped there and just focused on learning integration by parts. Like, really, that's our goal for the day, is learn integration by parts. And continuing on past that to actually plugging numbers in, that kind of took us away from our goal. So let's go back to just practicing integration by parts today. Because we can always plug numbers in later, which is just a matter of being very careful with the calculator. So let's go do more integration by parts. Shall we? Sorry for that complication. It's just wild how complicated it is to plug numbers in at the very end, isn't it? All right. So what we'd like to do, let me see here. What other problems we have? We've got that one to try, and that one. Oh, and that's it. So, okay, great. We just have 3 more. I'm going to save number 3, the natural log of z to the end, and let's go ahead and do 5 and 3, and then we'll go back and do 3. Okay, all the numbers are messed up. Let's go do these problems right here. So turn the page and let's try integration by parts 2 more times.
So number 5.
Yeah, the thing called number 5. All right, good. All right.
Oh, they're two.
Yeah, there are 2 number 3s. I need to go back.
Oh, they're different.
They are different. All right, so we have this integration by parts up here. And again, just looking at it, we don't know technically what order to put them in. So let's go ahead and leave it in the order that it's in and see how it goes. So the first thing is going to be our u. Second part will be dv. And we'd like to take the integral. Juan, have I really responded to your question now about which is which? Yeah, I mean, yeah, you just try it. So let's see what happens. So if we call that our u and our dv, I guess I'll just leave it here. So I'm gonna, there we go, make my box. Now I assume you're all drawing boxes, because you really can't do it without a box. I once saw someone try to do integration by parts without a box, and I was like, how do you read it? And I don't even know how you do it without a box. Okay, so u, derivative this way, antiderivative this way. And my u is natural log z. My dv is, oh now, should we write down the square root of z to the 19? How do we have to rewrite the square root of z to the 19? Yeah, so square root of z to the 19 is really z to the 19th to the power of 1/2, right? And if you have a power to a power, you multiply, so that's really z to the 19/2. Okay. Because in order to do the power rule, the anti-power rule, we just need a power, not a square root. So we're going to rewrite that as z to the 19/2. So that's z to the 19/2. Easy. Alrighty, everyone has the box. The first 2 pieces in it. You know, I'm confident that I'll never fall, but I can't say that the chair might not break. I mean, if the chair broke, I'd be really in trouble, wouldn't I? All right, so let's do it. The derivative of natural log is just 1 over z, dz. And then the antiderivative of z to the 19/2, you'd add 1. And remember, if you add 1, that's really adding 2 halves. So that's z to the adding 2 halves, 21 halves. Divide by what you get. Dividing by 21 halves is the same as multiplying by 2 21sts. Okay. Now, looking at that, you might say, Mr. G, that looks a little worse to me. It's not significantly worse. It's still just a power function, and the coefficient doesn't matter. Yeah?
Could you repeat what you did with the z to the power?
We're here?
No, I'm sorry, the 19,000.
Yeah, if you have z to the 19/2, you add 1, first of all, and adding 1 is really adding 2 halves. So that's z to the 21/2. And then you divide by what you get. And 1 divided by 21 halves is the same as 1 times 2 21sts, which is just 2 21sts. Does that make sense? Okay, we have all of our parts and pieces. Let us proceed. We start by writing down the integral of u dv equals u v minus integral v du. You always start by writing down the formula. That's the formula. That's the integration by parts formula. It's how we're rewriting a hard integral in terms of an integral we can do. Oh, yeah, there's no coefficient this time. That's nice. We don't have to worry about that. Okay, so from my box table, sure enough, it's the natural log z and z to the 19/2 dz. That's my original integral, except it's z to the 19/2 instead of the square root of z to the 19th. So now we can start rewriting it. So u, it's the natural log of z, times v, which is 2 21sts z to the 21/2, minus, now keep in mind that this part, it might look bad, but we don't have to do anything to it. It's already integrated. It's just a function. There's nothing else to do here. So that's fine that that looks terrible. Okay, so now minus the integral of v, which is 2/21 v to the 21 halves. du. And what is du? 1, oh, that's a z. Yeah, z. 1 over z. So what do you think, folks? Did we go from a hard integral that was not on our list of integrals we can solve to an easy integral that we can solve? Is that an easy integral? Well, we have to clean it up first. How does that get cleaned up?
First, kick it.
Yeah, certainly. Let's get rid of that coefficient. So there's natural log. Oh, I'm going to rewrite this whole thing now. That's 2/21 z to the 21 has natural log z minus, I'll take out the 2/21 integral, and now z to the 21 halves over z. What's that? Z to the 21 halves. The z, can't we push the z up into the numerator? What happens if I push this z to the 1 up into the numerator? It becomes z to the -1. And how do you multiply z to the 21 halves times z to the -1? Then you add the exponents. And so what's 21 halves minus 1, which is really 2 halves? Yeah, 19 halves. It returns back to z to the 19 halves. Easy. And sure enough, that is easy. We haven't done the integral yet. All we did was clean it up. All we did was clean that and combine them all together. So the only integral we actually have to do is z to the 19 halves. Again, this is interesting and fascinating, and why integration by parts is a big deal. We went from an integral that we had no idea how to solve because it's not on our list of simple integrals. We used a formula called integration by parts to rewrite it. At no point have we done an integral yet. Only now are we about to do an integral, and it's super easy. It's just an anti-power rule. So how do we take that integral? I'm going to rewrite this now. 2/21 z to the 21 minus 2/21. And the integral of z to the 19 halves is just the anti-power rule. So you add 1. So that means adding 2 halves, that's 21 halves. And again, divide by what you get. And if you divide by 21 halves, Josh, what's that the same as? Because this is a 1, and if we do 1 divided by 21 halves, that's the same as multiplying by 2/21. So now finally, we have 2/21 z to the 21 halves natural log z minus, this is really 2/21, so 2/21 squared. So that'd be 4 over 441 z to the 21 halves. Yes, plus a c. Now you'll notice why Wolfram Alpha is so excited about factoring. What can we factor? Instead of writing 4 over 441, I could have written 2/21 squared, right? So now what can we factor out of there? We can factor out 2/21 z to the 21 halves, and that would leave behind natural log z minus 2/21. And I can see why Wolfram Alpha would want to do that. That might feel simpler to factor out the common 2/21 fraction and the common z to the 21 halves. And now that we have done that, let's just check Wolfram. And I realize that's probably all we have to do today. So integral of natural log of x times square root of z to the 19. The answer they're going to give is that our answer? They rewrote it.
Really simple.
Look at all that 2/21 stuff. Did I type it in wrong? I typed it in wrong. Integral of natural log of x times the square root. Oh, I did type it in wrong. I did z times. Oh no, that's Maybe they don't know the square root. No, they must know the square root. The integral of natural log times the square root of c to the 19. How on earth is there no coefficient?
Why in the house?
Why what?
Are those graphs?
Yeah, those are graphs of the function. Wow, folks, I don't know how to explain this one. I don't know why they don't have any coefficients, but we do have coefficients. And our answer appears to be a little different.
We could do really to see if we're ready.
Yeah, we really should do the derivative to see if we're right. Our answer is similar because they do just have, that's the square root. Oh, yeah, no, it's a completely different fraction. Okay, well, I know that I'm out of time, so we're just gonna have to hold off on this one and say that we'll finish looking at it when we come back to class. Josh?
So with going back to the very top, the very first step, when you slide the and the DB,
Yeah.
could both ways
Work?
yeah.
It's an interesting idea. I don't know. I don't have an answer for you right off the top of my head. All right. That'd be pretty interesting. Okay, I'm gonna stare at it until I understand. Add 1, divide by what you get.
I have a question.
Yeah.
Over where you put the 1 over z in, into the 2 halves and then into the empty halves. Why do you write it back down the 21 halves?
Here? You mean in there?
Yeah.
Because then we actually do the integral. And then you add 1 and divide by what you get.
Mr. G.
Mm-hmm.
Are you familiar with Super Mario Quadratics?
Mm-hmm.
Sponsored by Desmos. It's like a little Mario game. Makes graphs.
Well, that sounds like fun.
Doesn't really apply to us, but if there's like a lower math class.
Well, that's fun. Send me an email about it so I can look it up. See you guys.
Yeah, to figure it out.
I don't know where their coefficients went.
Yeah, that wolf from Alpha, those Germans.
Yeah, you never know, right? You know what, Josh? Maybe it's wrong of me to assume that Wolfram alpha is correct. Because if I just do the product rule, the derivative of the first times the second plus derivative of the second times the first would give us z to the 19 has natural log of z minus 221st z to the 19 plus 221st z to the oh my gosh. Wolfram alpha is just incorrect.
Wow.
That just shook all my confidence, Joshua. Look at me. I assumed the Wolfram was correct and I was wrong.
But it turns out that the way that we did it on the board was correct.
Yes, it was correct. What the heck? I wonder if the way I write this down, but it just makes me so sad. I just let everyone think that we got it wrong. That I led them down the wrong tunnel. But it's not. See, look, they're still telling us the wrong thing. Now, how can I check that their answer is wrong? I would have to take the derivative of their answer and see if it's correct. So let's see. Well, their answer is awfully close to ours. Because my answer, or our answer, gosh, where's my answer? This thing? Here, yeah, it looks awfully different. If you factor out, I was already doing the product. No.
Wait.
Yeah, because they had this thing times natural log minus 1. So their 221st, they're calling a 1. Because if that 221st was actually just a 1 for some reason. Then they do have log minus 1. Let's say I have log minus 1. And over here, z to the 21 halves. Yeah, that's what's terribly wrong. They have x square root x to the 19 is actually x times x to the 19 halves, which is really 2 halves x to the 21 halves. Oh my gosh, so they really do have that. It's just that they have the wrong coefficient. That's blowing my mind. How can it be the wrong coefficient? And more importantly, does that coefficient not matter? I wonder if, okay, that's their answer. That's their answer. If we do the product rule, will we get the original? So the derivative of the first is the derivative of the first, which is 21 halves, z to the minus 1, 19 halves. Derivative of the first times the second, plus derivative of the second times the first. Okay, do we go back to the original? This would be 21 halves, z to the 19 halves, natural log z, minus 21 halves, z to the 19 halves, plus z to the 19 halves. Ha! Their way does not work, Josh. Okay, my mind is truly blown. That has shaken my confidence to the core, Joshua. I thought Wolfram Alpha is the place that you're supposed to be able to go to check your answer. You know what I did? Typed in a Z instead of an X. Is that a Z? I did. I mixed my variables. X. Survey says, oh snap, now it's correct.
It's just because we won.
One variable, because yeah, I use the variable Z, and Z typically represents imaginary complex numbers, whereas X is a normal variable. Now it's correct. Oh my gosh. Oh my god. Okay, well this is great.
So no one's wrong. It was just.
Nobody's wrong, except for me. I'm the only one who's wrong because I typed in a Z instead of an X. That's a good learning lesson because graphing calculators like Desmos, you can't just use any variable you want. You gotta use X and Y. Josh, thanks for sticking around. Oh my gosh.